All right, what's up, you guys? Hello. So here's me going over this study guide. I'm gonna go through and explain every problem, and I'm just gonna go in order. So if you just want to see one particular problem, then skip ahead to it. All right. So this first one says, find f of x if f prime is this function and f of 1 is 14. Okay. So you got the derivative, you want the original. That probably means you have to integrate, like anti-differentiate. Okay. F prime is, here's the derivative, 4x times x squared plus 1. All right, very cool. And then this will give me the antiderivative of f prime. Okay. And then we will, okay, so let's get that and then I'll say what to do. Okay, so if I want this derivative, you could do u substitution here. But I think it's less complicated if you just distribute this 4x. So let me do that. That would be 4x cubed plus 4x dx. Okay, and then you anti-differentiate. Antiderivative of 4x cubed is x to the 4th. Antiderivative of 4x is 2x squared. And then plus c. Okay, and then this plus c is the reason you need this like initial condition. You're going to use this to find out what the specific constant is for the particular function we're looking for. So what I mean is, this is f of x because it's an antiderivative for f prime. Now, if we take f of 1, which is what we were given, well, on one hand, that's us plugging in 1 into this function. So here's me doing that. 1 to the 4th plus 2 times 1 squared plus c. And on the other hand, the problem told us that f of 1 is 14. So that's also equal to 14. Cool. Okay, and then this is how we find c. We solve for c now. 1 to the 4th is 1 plus 2 times 1 squared is 2 plus c equals 14. This means 3 plus c is 14, which means that c is 11. So that's big, and now we know what particular constant is the function we're looking for. So this 11 goes in for c, and we get that our function is f of x equals x to the 4th times 2x squared plus 11. Cool. Okay, so you saw this problem a decent amount in the third homework from this unit. Okay, next is all about indefinite integrals. These are kind of out of order from how we did them like on the packet, but that's because I already had this review made from previous classes, or like a lot of it, and I didn't want to rewrite a whole review, so I just kept the same order. All right, so this first one is the indefinite integral of this stuff. This is the same thing as, just going to use a property here for integrals. That's the same thing as the integral of the first function plus a dx plus the integral of the second function. Okay. And then for this first function, like I already know whose derivative is 3 sine of x. That's just going to be negative 3 cosine of x. If you're thinking, wait, shouldn't that be positive cosine? No. Remember, you're thinking backwards. So you're thinking whose derivative is 3 sine of x? And that should be negative 3 cosine. Okay. Then I could put a plus c right here, but since I've got another derivative to do, or antiderivative to do, I'm just going to wait and do it at the end. Okay, antiderivative of this, I don't know it, but the natural thing to do here would be to split this fraction, so like x over x squared minus 12 over x squared. Okay, and then so now we have negative 3 cosine of x plus, oh shoot. Okay, sorry. Negative 3 cosine of x plus x over x squared is 1 over x. Negative 12 over x squared doesn't simplify, but you can rewrite it like this. 12x to the negative 2 so that it's easier to take the antiderivative of. Okay. Negative 3 cosine of x we have not messed with. Antiderivative of 1 over x is natural log of absolute value of x. Remember that. And then minus 12 times antiderivative of x to the negative 2. Well, this is just x to a power. So you add 1 to the power. Now it's negative 1, and then you divide by that new exponent. So over negative 1, and then the plus c. This time I do write it because I'm done anti-differentiating. Okay, cool. And now I am here. Negative 3 cosine of x plus natural log of absolute value of x. Then negative 12 over negative 1 is plus 12 x to the negative first, or 12 over x if you like that better. And then plus c. And that should be it. Yeah, okay. That's that. Next one. Says anti-differentiate x to the fourth minus cube root of x squared. That is just the same thing as integral of x to the fourth minus x to the 2/3 dx, which is, okay, these are just x to a power, both of these. So x to the fourth has an antiderivative of x to the fifth over 5, or 1/5 of that. Yes, I'll write it like that. And then same thing with x to the 2/3. So this would be minus x to the 2/3 plus 1 is x to the 5/3. And then divided by 5/3, or in other words, multiplied by 3/5. And then plus c, and that's it for that one. Okay, next one is pretty straightforward, even if it doesn't look like it. Antiderivative of 3 is 3x, and then this is exactly the derivative of arcsine. Well, 5 times arcsine, right? Because arcsine is 1 over 1 minus x squared, or the square root of that. So 5 over square root of 1 minus x squared is just 5 times this. So what I'm saying is, let me get rid of this. What I'm saying is this second part is just plus 5 arcsine, or sine inverse if you like that better, of x, straight up. And that's it, plus c. Yeah, not much else to do there. All right. Next one, also pretty straightforward. Both of these are straight up derivatives. The function whose derivative is cosecant squared is negative cotangent of x. Because if I had left it positive, then it would have been negative cosecant. But I want positive, so I got to account for that with the negative, with the extra negative. And then minus, this is just natural log of absolute value of x plus c. All right. Next one, also not too bad. You got the antiderivative of secant tangent. That is just straight up secant of x, nothing fancy to do there. This is x to a power, so same thing as before. You add 1 to the power and divide by it. So this divided by negative 1 would just turn this plus into a minus. So there's that. And then e to the x just is going to stay e to the x, whether you're differentiating or anti-differentiating. And then plus c. Nice. Then this one, there's maybe a temptation to do u substitution, but that wouldn't really help you out here, I don't think. Yeah, I don't think it would. So unfortunately, this one is all about foiling it and then anti-differentiating once you have a polynomial. So let's do that. 4x times 2x is 8x squared. 4x minus times negative 1 is minus 4x plus 6x would be plus 2x. And then minus 3. Okay, and then antiderivative of 8x squared is 8/3 x cubed. Hopefully you see how I added 1 and then divided by the new exponent. so x to the third over 3. Then antiderivative of 2x is x squared, and then minus 3x for the 3, and then plus c. Okay, nice. So that's it. That's the first page. We did it. Next one is all about the fundamental theorem. These will be nice because they are, I mean, they look really scary, but if you go back in your notes, you'll see they're not actually scary. The first part of the fundamental theorem says that if you differentiate an integral that is a constant as the lower limit and a x as the top limit, then you just put the x into the function. Basically, the derivative and the integral cancel each other out, and you just get the function back. In this particular case, however, we don't just have an x as the input of this like accumulation function. We have an x squared. In other words, we have a function within our accumulation function. So that should remind you of, when I take the derivative of that, function within function should remind you of chain rule. So what I'm saying is, okay, you take the derivative of this integral, it'll just kind of cancel. So I'll just be left with e to the 4 times x squared. You put this in for the variable. And then times, because of the chain rule, the derivative of the inside function, the derivative of this guy, this upper limit. So that would be derivative of x squared is 2x, and that's it. That's all you do. Nice. Okay, similar thing over here, but even easier because this is just an x. So fundamental theorem tells us the derivative and the integral kind of just cancel, and I just get back the cosine of x. I put this x into here, and that's it. That's all you do. Okay. Then this one is kind of tricky because the fundamental theorem tells us, okay, this derivative integral thing is true as long as you have a constant on the bottom and like as a lower limit and the variable as the upper limit. In this case, this is flipped. So you might remember from earlier in the unit that you're allowed to flip these bounds of integration as long as you make the integral negative. So that's what I'm about to do. I'm going to flip this 2 and 4x so that now my variable's up top. t cubed plus 2t dt. All right. And then now I can differentiate like I did with number 4 and 5 here. Remember, the derivative of something negative is just equal to the negative of that derivative. So I'll get negative. And then following the same rules as number 4 here, you just put this 4x in every t. So that would be negative 4x cubed plus 2 times 4x times the derivative of the inside of the 4x. So that would be a times 4. And then I guess you could simplify that, but I don't want to. So I'm just going to leave it like this. Well, let's not be lazy. I'll simplify this. This would be negative 4 cubed is 64, x cubed plus 8x times 4. And then that's as much as I want to do because I don't know what 64 times 4 is. Okay. Nice. Okay, then this is another nice one. This one we did a while ago, and it has to do with the fundamental theorem. In particular, it had, well, let me read you it. It says the graph of f prime, the derivative of f, is given below. If f of negative 2 is 6, what's the value of f of 2? Okay, so here we know nothing about the original function other than f of negative 2 is 6. More like we know a lot about the derivative and want to know something about the original f. Okay, so that sounds a lot like let's undo the derivative, which should sound like integration. So I'm going to integrate f prime. And then I want to know something about a specific value of f, meaning it would be helpful to do definite integration. And the only two bounds that I know for that I know anything about, like that the problem gave me any information on, is this -2 and this +2. So that's a good hint that, okay, I should go from -2 to +2. Okay, and why is this helpful? Well, watch this. The fundamental theorem tells you that when you integrate something from a lower limit to an upper limit, you get the antiderivative of the function inside, so that would be just f of x, evaluated at the top limit and the lower limit. In other words, this integral is equal to f of 2 minus f of -2. We know that like we've done this a lot of times with definite integrals. And look, this is helpful because that's almost what we're asked for. We're asked for the value of f of 2. Well, this is f of 2 minus a little bit. So if I just add f of -2 to both sides, then watch this, you guys. F of -2 plus this integral is equal to f of 2, exactly like we wanted. So that's how you solve this type of thing. We just have to figure out what this integral is, and we know what that is. This is just the definition of the area under this curve, or like between that curve and the x-axis. Okay, another way to think about it, if you want like just a quick like intuitive reason why this works, is that well, remember what an integral is. It just like accumulates all the change that's going on with f prime between -2 and 2. So in other words, it's the total change of f between -2 and 2. So where are we at f of 2? Like, what's our y value there? Well, if I know where I started at -2 and I add how much I changed between -2 and 2, then I'll end up with where I am at 2. So again, start plus total change will give me my endpoint, which is what's going on here. Okay, that's an intuitive definition either way, or an intuitive explanation. Either way, you should end up with this same expression here. So let's find out what that is as a number. First of all, I know that f of -2 is 6. So that would be 6 plus, okay, this integral is the area from -2 to 2 between the function and the x-axis. So this looks like a triangle, this looks like a triangle. Remember that if an area is below the x-axis, it'll be negative. So that would be, this has like a base of 2 and a height of -1. So that would be 2 times -1 over 2 for the triangle, plus this has a base of 2 and a height of 2. So 2 times 2 over 2. That will equal f of 2. And so therefore, this is what? 6 minus 1 plus 2 equals f of 2. And therefore, 5 plus 2, 7 equals f of 2. All right, we did it. Nice. Okay, next thing. Oh, sorry, y'all. Sorry, y'all. Nice. Okay, we're back. Next thing is a. Next thing is a bunch of definite integrals. So let me try to move this one more time. Yeah, okay. So definite integrals, remember, all the way to go about these is you anti-differentiate the function, then you plug in the top, you plug in the bottom, and you subtract the two. So here's what I mean. Antiderivative of this polynomial would be 2/3 x cubed minus 6x squared plus 13x. And then plus c if you want, but you don't have to do that with definite integrals because it would just end up canceling when you subtract your two values. So it's just, here's my antiderivative. I plug in 3 and 1, and I subtract the 2. So that's what this line means, evaluated at 3 and 1, and then you subtract the 2. So here's me doing that. 2/3 times here's me plugging in 3. Let me group that together so that I know what I'm doing. Okay, there's me plugging in 3 minus me plugging in 1. So let me group that together. Me plugging in 1. Okay, and then these look like they're going to be ugly numbers. Yeah, I don't know how much I want to simplify this, but let's just see what we get. This would be, let me do some tricks here. 2/3 of 3 cubed, well, 27 over 3 will be 9, times 2 will be 18, minus 6 times 9, what's that, 54, plus 13 times 3 is 39, yikes. Minus, okay, and then these will all just be the coefficients because this will be 1, so this will be 2/3 times 1. This will be minus 6 times 1, so minus 6, and then 13 times 1. So 13. Nice, okay, and then you just find out what this is. I don't want to do that though, so here's my calculator. Okay, 18 minus 54 plus 39 minus 2/3 minus 6 plus 13 is, well, you can't see that, but that's negative 4.6667. So that's what? Negative 4 and 2/3, which would be negative 14 over 3. Is that right? Negative 14 over 3 is that. Yeah, okay, good job. Cool. Okay, same thing for all these other ones. So let's try to do these. Antiderivative of this polynomial would be negative 1/4 x to the 4th plus 3/2 x squared minus 2x plus c if you want, but again, you don't have to do that for definite integrals. Evaluated at 3 and 0, I plug in 3, I would get 3 to the 4th plus 3/2 3 squared minus 2 times 3 minus, okay, and then this will be nice because me plugging in 0 will just be 0, 0, and 0. So minus 0. Cool. So I just have to find out what this is. I don't want to do that though, so I'll let my calculator do it. On a test, by the way, if you get something ugly like this, then don't even try to simplify it. Like, just circle this and move on. But let's get a nice answer since I have my calculator out already. This would be negative 1/4, negative 1 over 4 times 3 to the 4th plus 3/2 times 3 squared minus 2 times 3, which is 6. Okay, negative 12.75, which is negative 51 over 4, I believe. Yeah, cool. So negative 51/4 for that one. Remember what this means is that since we got negatives for both of these, the area between the curve and the x-axis for these is mostly under the x-axis. So I don't know what this function actually looks like. I just know it's like some sort of parabola. So from 1 to 3, it is mostly under the x-axis. It might look something like this. Okay, just a conceptual explanation of what's going on there. Okay, next one. I hope this camera doesn't fall. I'm holding it. I'm holding it. Okay, we did good. All right, next one. Okay, so this is the first one where it's not like super clear what this derivative would be. Natural thing to do would be split this fraction. So let me try that. We're going from 1 to 4 of x over square root of x minus 7 over square root of x dx. Okay. Then, well, this denominator is just x to the 1/2. So let me maybe write that down. I hope I don't take up too much room because I don't have that much room to work with. Okay, and then x to the first over x to the 1/2, you're just subtracting the exponents now. This is 1 to 4. 1 minus 1/2 is just x to the 1/2. And then 7 over x to the 1/2, that's another way of saying 7x to the negative 1/2. Okay, and the benefit of writing it like this is now this is x to a power, this is x to a power. Those are easy to take the antiderivatives of. So here is me doing that. To take the antiderivative of x to almost any power, like any power other than -1, you add 1 to this exponent, so that would be x to the 3/2. Then you divide by the new exponent. So dividing by 3/2 is the same thing as multiplying by 2/3, and there's my antiderivative for that. Minus 7 times same thing here, x to the negative 1/2 plus 1 is x to the 1/2. Then dividing by 1/2 is the same thing as multiplying by 2. And I'm evaluating that at 4 and 1. So let me kind of simplify this. This would be 2/3 x to the 3/2 minus 14 x to the 1/2 at 4 and 1. Okay, so now I just plug in my 4, plug in my 1, and subtract the 2. Nice thing is that both of those are perfect squares. So let's see what we get. This would be 2/3 times 4 to the 3/2 minus 14 times 4 to the 1/2. That's me plugging in 4 minus me plugging in 1 would look like this. Okay, and then whatever number that gives me will be my answer. Again, on a test, if you circled this, I would give you full credit. But okay, let's find out what this is. Yikes, what is 4 to the 3/2? I guess that would be the square root of 4 is 2, cubed is 8. And then times 2/3 would be 16/3 minus 28, because the square root of 4 is 2 times 14 is 28. And then minus 2/3 minus 14. Okay, I do not want to mess with that, so let me have my calculator mess with it. That's 16/3 minus 28 minus 2/3 minus 14. That is negative 9 1/3, which would be what? Negative 28/3. Nice. Is that right? Negative 28/3. Yeah. Cool. Okay. Next one. Okay. Thankfully, it's like a pretty quick and simple one. Antiderivative of 2e to the x is 2e to the x, evaluated at 0 and -3. I plug those in, I get 2e to the 0 minus 2e to the -3rd. 2e to the 0 is just 2 times 1, and then minus, well, there's not much to do here. You could write this as 2 over e to the 3rd, but that's as simple as it can get. I'm going to circle that and move on. That's nice. Next one, also straightforward. Antiderivative of secant squared is tangent, so 2 times tangent of x. Evaluated at pi over 4 and negative pi over 4. Okay, if you remember your unit circle, tangent of pi over 4 is 1, so 2 times, well, let me write the in-between step. Here's me plugging in pi over 4 minus me plugging in negative pi over 4. Okay, like I said, tangent of pi over 4 is 1, so 2 minus tangent of negative pi over 4 is negative 1. So minus 2 times negative 1 would be minus negative 2. In other words, 2 plus 2, which is 4. So this is kind of a wild one because this is such a crazy looking function, and you're being asked to take the area between negative pi over 4 and pi over 4 of this crazy secant squared function, which I don't really even know what that looks like. But if you graph this on Desmos, you'll get something crazy. And what this is saying is that the area under that is exactly 4 units, which is kind of wild. All right. By that, I mean you don't need to know that. You just need to know how to do this, but that's an interesting little thing. Oh my god. Sorry, y'all. This is my setup right now. I've got this on top of a little speaker, and so anytime I move the speaker, this falls off of it. Okay. Next one, okay, same thing, anti-differentiate, plug in your limits, and then subtract. Let me rewrite this integral as 1 to 3 of x to the negative second plus x to the negative 2/3. That way it's just x to a power. And when I anti-differentiate, I get x to the, add 1 to this would be x to the negative first. And then dividing by negative first will just make this negative. And then plus x to the, add 1 to negative 2/3, you get 1/3. And then divide by this 1/3, that's the same thing as multiplying by 3. And I'm plugging in 3 and 1 into that. So when I plug in 3, I get negative 3 to the negative first, which is just 1/3, plus 3 times 3 to the 1/3. How do I want? Let me just write that as cube root of 3. Minus, and then me plugging in 1 will just be 1 to the negative first will be negative 1 because of that negative. And then me plugging in 1 into here will just be 3 times 1. Okay, and then maybe that's as simple as I want to make it. Well, no, let's make it a little bit simpler. This is negative 1/3 plus 1 minus 3. So plus minus 2. Negative 1/3 minus 2, negative 7 over 3 plus 3 cube root of 3. Okay. I think I did that right. And if I did, then that's your answer. Okay. Next. Okay, next is all about U substitution. All right. So U substitution, remember this is undoing the chain rule, so you have to find a good U whose derivative is also being multiplied in the integral. So here I see a natural log of x squared over x. Here you kind of have two choices for what U should be, but if you choose this x down here, then that would be, or like this 1 over x, then that won't really help you very much. I have a lot of experience, so I know for sure, like just by looking at this, that the U should be natural log. Because then when I take my du, I get 1 over x dx, which is exactly what's left over. Like that's what I want to replace. All right, so then this integral becomes not natural log squared, but we called natural log u. So u squared, and then this over x dx is all taken care of by the du. Okay, and now my integral is that, which looks very tame. I know what the antiderivative of something squared is. It is 1/3 u cubed plus c. And then if I started with x's, probably I want to end with x's. So this would be 1/3 natural log of x all cubed plus c, and that's it. Nice one. All right, next one is e to the 2x. The only reason this needs u substitution is because, like, I know what the antiderivative of e to the x is, but not e to the 2x. So I just want this to be just an like e to the u. So this one should be, your u should be 2x, your du would be 2dx. But I'm not trying, like, my leftovers aren't 2dx, I'm just trying to replace 1dx. So I'm going to divide by 2 on both sides and get that 1/2 du is equal to dx. Cool, okay. Then I go in to replace my stuff. I get e to the 2x we called u, so e to the u, and then dx was 1/2 du. I'm going to put the du in here and the 1/2 out here to start with. And then this looks like something I can take the antiderivative of. So that would be 1/2 e to the u plus c. And then going back to x's, once we've anti-differentiated, you would get e to the, what do we say you were? Here it is, e to the 2x plus c. Okay, and remember you can check any of these just by like taking the derivative of whatever your answer is. And if you get back to the original, then you did something right. Okay. Next one. Okay, so this one is the first one that might look kind of crazy, like what do I pick for my u? Remember, your first choice should always be whatever looks like an inside function, as in this stuff in parentheses looks kind of suspicious, like it's inside something to the 10th, and I see its derivative here, or at least a constant multiple of its derivative. So that's a good hint, like that for sure, it's got to be my u. So I'm saying u should be 2x cubed plus 5. That way du is 6x squared dx. However, I'm not trying to replace 6x squared dx. I'm just trying to replace 1x squared dx. That's my leftover bits after I pick my u. So I want to get rid of this 6. So I divide by 6 on both sides. 1/6 du is equal to dx. No, sorry, x squared dx. Okay. And now that's exactly what I have left over, so I'm good to start replacing, like substituting stuff. Okay, I had u to the 10th. This x squared dx is all picked up by the 1/6 du. So du I'll put in the integral, 1/6 I'll just put outside. And then now this looks like a very tame thing. That's just 1/6 times u to the 10th has an antiderivative of u to the 11th over 11, and then plus c. Let me do two things at once now. 1/6 times 1/11th is 1/66. U to the 11th, we said u was 2x cubed plus 5. All to the 11th, and then plus c. There's my antiderivative. All right. Next is this 3x squared over x cubed plus 4. Hopefully you see that the u in this case should be this bottom, this denominator, because again, I see its derivative being multiplied in the integral. If you pick u to be x cubed plus 4, then the du is exactly 3x squared dx. That's the derivative of this. Cool, I see exactly 3x squared dx. That's exactly what I want to replace, so I don't have to do anything, like I don't have to divide by anything or anything. This is just ready to be replaced. So the 3x squared dx will all be taken care of by the du, and then I have 1 over u as my integral. That is the natural, like the antiderivative of 1 over u is the natural log of the absolute value of u, plus c, which we called u x cubed plus 4 plus c. Nice. All right, okay, making progress. Okay. Next is, okay, this sine cube function. Sorry, I got distracted. I was looking at my TV. Somebody did a cool ski trick on the Olympics. But okay, anyway, this is sine cube times cosine of x dx. This one, it might be kind of tricky to pick your u because the derivative of cosine is negative sine and the derivative of sine is cosine. So how do I choose what my u should be? Remember, your u should be your inside function whose derivative is also in the thing. So I see sine is inside an x cubed function, so that should be my u. That way my du is cosine of x dx. That is exactly what I'm trying to replace, so I don't need to divide by 2 or anything like that. Now I just get into okay, now I just get into replacing the stuff in my integral. So that should look like sine we called u, and that was sine cubed, so u cubed, and then du takes care of this cosine of x dx, the whole thing. All right, and then the antiderivative of u cubed is just u to the 4th over 4 plus c. U to the 4th we said would be sine to the 4th of x dx plus sine to the 4th of x over 4 plus c, and that's your derivative. Or sorry, your antiderivative. Okay, now is u substitution with definite integrals. So you got 2 options for how to do these. One option is like let's do it like this. 18 will do it one way, 19 will do it the other way. Those are your 2 options for how to deal with u substitution with definite integrals. The first option is just to do the normal thing like you've always done it. Go back to x's, like do your u substitution, get your antiderivative, go back to x's, and then plug in your stuff. The other way would be to change your bounds into u, like, because right now these are x values, 0 and 1/4 are x values. So when you go to u's, you could change all these bounds to u values, and then you don't have to go back to x's. They're both the exact same amount of work. One just front loads the work, and the other one leaves the work until the end. So let's do this first one in the natural way. Let's just do it the same way we've always done it. Go back to x's, and then plug in our stuff. Okay, so sine of 4x. I know what the antiderivative of sine of x is, but not 4x. So I need to do some u substitution. If I make u be 4x, then my du would be 4dx. But the leftovers I'm trying to replace is just 1 dx, not 4 dx. So that should be 1/4 du is equal to dx. Okay, now I go into replacing this integral. Now for a second, I'm just going to make it an improper integral because, again, when I go to u's, these bounds are x values, and I'm talking about u's, so I can't keep the same bounds. So what I'm saying is I'm just going to replace this with an indefinite integral, get the antiderivative, and then go back and plug these values in. Okay, so integral of sine of 4x we called u, and then dx was 1/4 du. So I'm going to put the du in here, the 1/4 out here, take my antiderivative, which would be 1/4 times negative cosine of x, no, whoops, sorry, of u. And then you could put a plus c. Actually, yeah, let me be consistent and put a plus c. Okay, and then now let me go back to x's. Or let me simplify this as well. This would be negative 1/4 cosine of, we called u 4x. And then let me ignore this plus c because it's going to cancel out anyway. And now that I'm back to x's, now I can plug in my bounds of integration. pi over 4, and 0, which were x values to start with. Okay, so now I plug these in. These become -1/4 cosine of pi over 4 times 4 would just be pi. There's me plugging in pi over 4 minus -1/4 cosine of 4 times 0 is 0, so 0. Okay, and then -1/4 cosine of pi, well, cosine of pi, depending on how much you remember about the unit circle, cosine of pi is -1 times -1/4 is 1/4. And then minus -1/4 cosine of 0 is just 1. So this would be minus -1/4. In other words, plus 1/4. That would be 1/2 as your answer. Okay, so that's one option for definite integrals with U substitution. The other option looks like what we're about to do here. So remember in 18, we went to an indefinite integral and went back to x's and then plugged in our stuff. The other option is to do U substitution with even the bounds. So what I mean is, okay, sorry, I was just trying to figure out what my U should be, and I think I have it. This kind of looks like it could be a arcsine function, but because of this 8x, it's just a normal U substitution problem. So you should choose your U to be 4x squared. Sorry, 1 minus 4x squared. That way your du is -8x dx because of this negative right here. All right, but I just see a positive 8x dx right here, so I'm going to make -1 du is equal to 8x dx. Okay, now you replace your integral. And okay, this 8x dx will be taken care of by this -1 du, so I'm going to have 1 over square root of u, and then times -1 du. So du I'll put here, negative I'll put out here. And my bounds of integration, I'm going to take them from x values right here, 0 and 1/4, to u values by putting them through this u equation. So what I mean is if I put 0 in for u, I would get 1 minus 4 times 0 squared is just 1. So my bottom bound was a 0. After I made it a u, it became a 1. And then my top bound would be 1 minus 4 times 1/4 squared is 1 minus 1/4, which is 3/4. So my top bound became 3/4. Then if you're thinking, wait, Mr. Cordero, you did something wrong. Shouldn't it go small to big? Yeah, normally it should, but after U substitution, some things can get wacky. So this is fine that we're going from 1 to 3/4. If it makes you uncomfortable, like as much as it makes me uncomfortable, then remember you are allowed to switch these bounds to make it small to big, 3/4 to 1, as long as you take the negative of that integral. And so, since my integral was already negative, and I take the negative again, now it becomes a positive integral of 1 over square root of u du. Okay, the benefit of doing this, changing your bounds to u values, is that now at the end, I don't have to go back to x's. I can just plug in my values straight into the u, which is like, saves a little bit of time, but then we also have to do this extra work out front. So it's exactly the same amount of work. Okay. All right, let's do this. This is the integral from 3/4 to 1 of 1 over square root of u is the same thing as u to the -1/2 du. Okay, antiderivative of that would be u to the positive 1/2 because add 1 and then divide by this 1/2 is the same thing as multiplying by 2. Plus c, but you don't need that, remember, for definite integrals. And since I already changed these to u values, I can just plug in my values straight up, 1 and 3/4. Okay, if I plug in 1, I get 2 times 1. If I plug in 3/4, I get 2 times 3/4. 2 times 1 is 2. minus 2 times 3/4 is 6/4, which is 3/2. So 4/2 minus 3/2 is 1/2. Okay, we got the same things up here. That's kind of wild. Cool, neat. All right, and then this last one, I hope to God this camera doesn't fall. Okay. This last one, you might just, like, if you memorize the formula, you don't even need to do some U substitution here, but I never memorize this formula. I always have to go through the whole process. So let's go through the whole process. Okay, this right here should remind you of an arctangent function. Arctangent has the derivative, where do I write it? Right here. 1 plus 1 over 1 plus x squared. There it is. Okay, this is 1 over 9 plus x squared. So I wish I could turn this into a 1 over 1 plus x squared somehow. Okay, the way to do that without altering any values or anything is to make a new function and say, oh, I wish this x squared was 9x squared. That way I could factor out the 9 and end up with 1 plus x squared. So, okay, let's force it to be that. Let's say I wish x squared was 9u squared. Okay, then if I want that to be true, then what does u have to be? Well, let's find out. If I divide by 9, I get 1/9 x squared equals u squared. And if I take the square root of both sides to find out what u is, I would get 1/3 x equals u. Cool. So there's what u will be. Then I take the du, I get 1/3 dx equals du. But I'm not trying to replace 1/3 dx, I'm just trying to replace 1 dx. So times 3, I get dx equals 3 du. Okay. Now I'm almost out of room, so I hope I can fit this all. But now that I have all of this stuff, I can replace my integral with the integral from the integral of 1 over 9 plus x squared we said was 9u squared du. Oh, but wait, dx was 3 du, so 3 out here. My mistake. Okay, sorry. Now we're here. That makes this 3 times the integral of 1 over, here is me factoring out a 9. And I'd be left with 1 plus u squared du. And then look how close that is to the arctangent guy, the arctangent derivative. It's just this extra 1/9 in the way. And one, like a constant multiple in a integral is no big deal. You can take that out. So let me do that. If I take out 1/9 from this integral, I'd be left with 3 times a 9th, which is 1/3. And then the integral. Okay. And then okay, now I have exactly the the derivative of arctangent. So if I take the antiderivative, I get 1/3 arctangent of u plus c. And then what did we say u was? This would be 1/3 arctangent of u was 1/3 x. So, or x over 3 to save space, plus c. And then that's your answer. Okay, cool, so there's that. All right, next is, oh boy, completing the square and stuff like that. All right, let me just see how much I have left. That, and then definitions, and that's it. Okay, all right, we're almost close. All right, completing the square. For completing the square, you're always going to get either an arctangent or an arcsine. Like, I can't think of an example where you wouldn't get that. Okay. So let's do this first one. All right, this first one, completing the square on this, I should end up with an x minus 7 squared plus some stuff. Okay. So remember, the way I like to complete the square is I think, okay, what would it have to be if I did get x minus 7 squared? As in, if I were to FOIL this all out, x minus 7 squared would give me x squared minus 14x plus 49. Oh, one more thing. Remember how I got this minus 7 is taking half of this middle term. So that was a minus 14x, half of 14 is 7. So I know that completing the square will end up with x minus 7 squared. Okay, now x minus 7 squared is x squared minus 14x plus 49. Okay, so if I'm to complete the square on this, then yeah, let me do it off to the side and then mess with the integral in a second. If I'm going to complete the square on this, okay, then I'm going to need an x squared minus 14x plus 49 that I can factor into this x minus 7 squared. But this completely changes the value of the denominator here of this polynomial. I didn't start off with x squared minus 14x plus 49. I started off with x squared minus 14x plus 58. And so if I force out of 49, like if I want to write it as x squared plus minus 14x plus 49, then I still need to get back to this 58 by adding an extra 11. Because 49 plus 11, nope, sorry, that's wrong. 49 plus 9 would get me back to this 58. Okay, so what I'm saying is you can force this polynomial to be in this polynomial by splitting this 58 up into a 49 and a 9. That's all I did. And then this I can factor into x minus 7 squared. Okay. So if that did not make sense, then watch the next one. I'll try to re-explain it in a better way. All right, but completing the square on this integral, I would get 1 over. All right. This x squared minus 14x plus 58, we know we can write it as x squared minus 14x plus 49, and then plus 9. Now, this x squared minus 14x plus 49, we know can factor. The whole point of writing it like that was so we could factor it like x minus 7 all squared. So we'll be left with x minus 7 all squared plus 9. So that's what will go down here. Okay, and now this should look a little bit like this arctangent thing. Let me erase this so I don't confuse people when I post the key on Schoology. Like I was saying, this fraction here, 1 over something squared plus 9, should look a lot like arctangent, 1 over something squared plus something. Okay, the only thing is that I wish this was just a u squared, and I wish this was just a 1. So the way to get that is to do some u substitution. Okay, now let me erase this just to make some room. This is just side work. And then here is what I mean by u substitution. If I want to factor out a 9 and get the exact arctangent like formula, then I would need 9u squared to be equal to x minus 7 squared. That way I would have a 9u squared down here. I could factor out a 9, and we'd follow the same steps as number 20 up here. Okay. So if I want that to be true, then what should u be? Well, let me divide by 9. I get u squared equals 1/9 times x minus 7 squared. Taking the square root, I get u equals 1/3 times x minus 7. Therefore, du should be the derivative of this, which would just be 1/3. Yeah. If you don't see that, distribute this 1/3, take the derivative, you'll see it's 1/3. Cool. Okay. And then last thing, I don't want to replace 1/3 dx. I only see a dx, so let me multiply by 3 on both sides. I get I get 3 du equals dx. Okay. And now it's just about u substitution, just like we did with number 20 here. So okay, let's go through that. This will be integral of 1 over this we force to be 9u squared plus 9 du. And actually this dx is actually 3 du, so let me put a 3 out here. Okay, and now you see why I did what I did. I made it a 9u squared so that I could factor out a 9 just like a number 20 up there. 1 over 9 times u squared plus 1 du. Now I can take out this 1/9 from the integral. So 3 times a 9th is a 1/3 again, just like in number 20. All right. Then I got 1/3 times the arctangent of u because that's the antiderivative of this. 1/3 arctan of u plus c, and then arctangent of u, we called u, what is it? Oh, u was 1/3 x minus 7. So our final answer will be 1/3 arctangent of x minus 7 over 3 plus c. Nice. All right, we did it. So that was all one problem. If you kind of know what to look for, though, it shouldn't take that long. I was just explaining all the steps. All right, so there's 21. 22 will be the same exact way. So let me go through it at a little bit of a faster speed. I want to complete the square on this. Actually, is 78 divisible by 6? I think so. 78 by 6, 13. Okay, thank God. So here's what I'm going to do first. I'm going to factor out a 6 out of all these, just to make these numbers easier to deal with. So that will become 1 over 6 times x squared plus 6x plus 13 dx. Okay, then this 1/6, let me put it out in front of the integral so that it's not like confusing me. So 1/6 integral of 1 over x squared plus, what did we say, 6x plus 13 dx. Okay, now this is 1 over some quadratic trinomial. Okay, that is a good hint that I need to complete the square. Okay, how do you complete the square again? Well, remember, your goal is to get x plus something all squared, x plus something all squared plus some leftovers, some remainder stuff. Okay, in this particular case, I need my x plus something to be x plus half of this every time. It's always half of your x term. So the x term is 6 in this case, half of that would be 3. So my end result after completing the square will be x plus 3 squared plus some leftover stuff. Okay, how do I figure out this leftover stuff? Well, you FOIL this all out, and then you see how much you have to take out of 13. Okay, so here's what I mean. Let's do it over here, some side work. Okay, if I FOIL out x plus 3 squared, I get x squared plus 6x plus 9. Again, that is x plus 3 all squared. All right, so that's what I want to be, that's what I want to force to be down here in this denominator, okay? But I started off with a plus 13, not a plus 9. So if I don't account for that, then I've completely changed the integral. I don't want to do that. I want to keep the value the same. So to get back to this 13, I would need a plus 9 plus 4 more to get back to 13. Okay, so that determines this leftover bit. So that my bottom, after I do some completing the square, I'll end up with x plus 3 squared plus 4. Okay, hopefully that makes a little bit of sense. Again, complete the square by seeing what half of the x term is. That would be a 3. So therefore, after completing the square, you will be left with x plus 3 squared plus some leftovers. Okay, what is this leftover? You square this all out, end up with x squared plus 6x plus 9, and then you want to get back to this 13. So x squared plus 6x plus 9 plus 4 would get me back to that 13. So your leftovers are this. All right, so now into this. I complete the square on the bottom, and I already see what I'm going to get. I already did all the hard work. That would be x plus 3 all squared plus 4 dx. Cool. Okay, and then you follow the same steps as over here. So now I want this x plus 3 squared to be 4u squared so that I can factor out that 4. So let me force that to be true. 4u squared has to equal x plus 3 squared. All right, so what does u have to be? I divide by 4. I take a square root. I get 1/2 x plus 3. And then I get my d, so there's my u, and I get my du by taking the derivative, which will just be this number out here in front, 1/2, and then dx. Nice. Then I can go into replacing this stuff. Oh, actually, hang on 1 second, sorry. I want to replace dx, not 1/2 dx, so I multiply by 2. I get 2 du equals dx. Okay, now I go into replacing everything with u's, so I get this 1/6 integral of 1 over x plus 3 we said was, x plus 3 squared we said was 4u squared plus 4. And then dx was 2 du. So du I'll put in here. Times 2 I'll put out here. All right. Now 2/6 is 1/3. Let me do two things at once. So the 2/6 is 1/3. Then I'm going to factor out this 4 from the denominator here. Be left with that. Then I'm going to move the camera a little bit. Now I can take out this 1/4. So 1/3 times another 1/4 is 1/12. Integral of 1 over u squared plus 1 du. That would give me 1/12 arctangent, because the antiderivative of this is exactly is exactly arctangent of u plus c, and then this is 1/12 arctangent of what did we say u was? Here it is. U was half of x plus 3, so x plus 3 over 2 plus c. And then we did it. We got that one done. Okay. All right, last completing the square one. Here it is. Sorry, I got distracted again. I looked at the TV. Here's the last completing the square one. Oh boy, I hope we have room. Okay, so first let me do the side work, completing the square on this. First of all, notice it's got a little square root and a negative x squared, so probably this is going to be an arc sine one. Okay, first let me complete the square on this. Okay, here is my polynomial, negative x squared minus 6x plus 40. Let me get the camera set up good. Okay, minus 6x plus 40. Okay. Then, this always messes me up. So let me take out this negative just so that it's a positive x squared. You don't have to do this. I just always have, like, this messes me up when I have to complete the square and there's a negative out in front. So take out a negative, x squared plus 6x minus 40. That will change the sign of all these. Okay, then if I'm trying to complete the square on this, then I know I need half of this, like my result will be x plus half of 6 is 3 squared plus some leftovers. Okay, now what would this factor all out to be? Or sorry, what would this FOIL all out to be? Well, x plus 3 all squared would be x squared plus 6x plus 9. But I need to get back to this minus 40. So to get from positive 9 to negative 40, I need to subtract off 49 more. Okay, so after completing the square and everything, I would end up with x plus 3 squared minus 49, because all of this just turns into x plus 3 squared. So minus 49. Yay. Okay, and then remember, okay, so I should have been more careful, because remember I had a negative in front of this whole thing. So that would be negative this whole thing. And so therefore negative this whole thing. Sorry. And then that means if I distribute this negative back in, just to like not deal with an extra negative, then I would end up with a positive 49 minus this x plus 3 squared. 49 minus x plus 3 squared. All right. Hopefully you were able to follow that. Sorry about me forgetting that negative. All right. So there's me completing the square. That's good news. Now I can go in and replace this integral with the completed square one. That would be 1 over square root of, we said this polynomial is equivalent after completing the square to 49 minus x plus 3 all squared. Cool. Now, I would like this to be a 1 minus x squared. So I'm going to have to factor out this 49. So just like in the previous ones, I'm going to force this x plus 3 squared to be 49u squared so that I can factor that out. Cool. So if I want this to be true, then what does u have to be? Well, let's find out. Divide by 49 on both sides. Get that. Take the square root. You get this. Okay, and then take your du. You'll get 1/7 dx. If you're only trying to replace dx and not 1/7 dx, then you multiply by 7 on both sides, and you get the du, or sorry, 7 du is equal to dx. And now I believe the hard part is done. Now we just have to like plug in the right numbers, substitute in the right stuff. Okay, so you take a break, you stretch out your hands, and then you replace all this stuff. So this would be the integral of 1 over square root of 49 minus, we forced this x plus 3 cubed to be 49u squared. Okay, and then dx was 7 du. So du goes in here. I take the 7 out right away. You don't have to, I guess. Okay, then we factor out the 49. We get 7 times integral of 1 over square root of 49 times 1 minus u squared du. And then look, now I can take this part, the 1 over square root of 49, out of the integral, just like we did with the arctangent ones, but now with an extra square root. And that's legal because the square root of something times something is equal to the square root of factor times square root of factor. Okay, so let me do that. Square root of 49 is 7. If I factor that out of, or if I like take this out of this integral, then I'll be left with 7 times 1/7, which would cancel. So I'm just left with a 1 out in front, then integral of 1 over square root of 1 minus u squared du. That is exactly equal to the arc sine of u plus c. And then we said that u was this guy, x plus 3 over 7. So this becomes arc sine of x plus 3 over 7 plus c. Yay! All right, we've done it, you guys. There's all that. Now let me drink some water, and then we'll go on to the last little bit. Okay, Riemann sums. Let me move this. Riemann sums, these you guys were really good at, like even from day one. So hopefully you haven't forgotten what these are like. These are like you're trying to estimate the area under here. These were before we knew how to actually find the exact area by anti-differentiating. The best we could do is just make a bunch of little rectangles and approximate the area. So okay, so a left Riemann sum means, remember, the height of each rectangle is defined by the left endpoint. And then it wants 5 equal rectangles. So, okay, it looks like going from 0 to 1.25 with 5 equal rectangles. Each rectangle should be 0.25 in length. That's just me doing 1.25 divided by 5. That's exactly equal to 0.25. I didn't actually know that. I just looked at this graph and I was like, oh, this would be 1 rectangle, 2, 3, 4, 5. Okay, but all right. Let's do it. So left Riemann sum. This first rectangle has a left endpoint at 0. So from 0, this is me doing the left Riemann sum. That's why I'm saying left endpoint. Okay. So from 0, the left endpoint, I go up to my function, stop when I hit it, and that's my height for the entire rectangle. Next rectangle, 0.25 to 0.5, has a left endpoint of 0.25. So from there, I go up to my function. That defines my height. Next rectangle, look like this, 0.75. Like this. Notice I go a little bit over. That's okay. These didn't go over. These left some leftover room. And then from 1, I go up, and that's my height for that rectangle. And now you just find the area of this rectangle, this one, each rectangle, and add them all together. Okay, so let's do that. That would be, okay, base is 0.25 times height is 10 for the first one, plus base is 0.25 for the next one, height is 20, plus base is 0.25 for the next one, height is 50, plus base is 0.25 for the next one, height is 60, plus 0.25 times height is 50 again, I think. I don't know if that's exactly 50, but I'm just going to call it 50. Okay. Cool. Then you find out what this number is, and that's it. Let me also say one thing that I may or may not have said in class, but notice all of these have a 0.25 in front of them. So you could factor that all out and write it as 0.25 times 10 plus 20 plus 50 plus 60. So I might do that for the next one just to make it less writing. Okay, but for now, this is what we've got. I'm going to add all those up. So 0.25 times 10 plus 20 plus 50 plus 60 plus 50. Is that 5? 1, 2, 3, 4, 5. Okay, yes. And you would get 47.5. And that's your approximation for the left Riemann sum. Right Riemann sum is similar, except now you use the right endpoint of each rectangle. So that would mean, let me see if I got a different color. All right, we'll do this one in green. Okay, for the right Riemann sum, this first rectangle has a right endpoint of 0.25. So from there, I go up to my function, and that's my first rectangle. Then my next right endpoint would be at 0.5. That's my next rectangle. Then 0.75, that's my next rectangle. 1, that's my next rectangle. 1.25, that's my next rectangle. Okay, so now let me move my camera a little bit. All right. So I get the area of each of these by doing base, which each of them will have a base of 0.25. But here's what I was saying before. They'll all have a base of 0.25, so they'll all be multiplied by 0.25. So let me just write that once. Let me factor that out of each of them. 0.25 for the base times, oh, this is running out of ink. Let me finish this in, well, let me see if I can get ink out of this. Times, okay, the height of the first rectangle is 20. Plus, height of the second rectangle was 50. Third was 60. Fourth was 50 again. And fifth was about 40. It wasn't exactly 40, but I'm just going to call it 40. You can you can kind of approximate. I don't know what exactly that number is. On the test, it will either be exact, like we'll tell you exactly what the heights are, or you can just approximate. All right. All right, putting this into my calculator, 0.25 times 20 plus 50 plus 60 plus 50 plus 40, you get 55. So that's your right approximation. Okay, now you drink some water. Okay, and then you do the trapezoid sum. Okay, remember how trapezoids work? If I draw a sample trapezoid like this, then the area of this would be, if I call this B1, B2, and H, the area of this is H times B1, the average of the two bases. So B1 plus B2 over 2. Okay, so in this particular case, how do you get each height? Well, remember, you go from the left and from the right, get each of those heights. Those define your two bases. So your trapezoid looks like this. Then same thing for this one. Go up from the left, up from the right, connect them, and that's your trapezoid. Up from the left, up from the right, connect them, that's your trapezoid. Up from left, up from right, connect them, that's your trapezoid. Left, right, connect, trapezoid. Okay. So these will all have a width h of 0.25. The first trapezoid has a left height of 10 plus a right height of 20 over 2. Next one, also a height, or a base of 25, left height of 20 plus right height of about 50 over 2. Next one, 0.25 times, where were we? So we've done this one, we've done this one. Next one would be 50 and 60 over 2. 0.25, done this one. 60 and 50. Okay, now I've done this one, and last one would be 0.25 50 and 40 about. All right, you put this into a calculator and you get a number. Let's try to do that real fast. Okay, if I put this in right, then I got 51.25, which seems about right according to these other ones, like it's pretty close to these other ones. So I'm gonna guess I put it in right. If not, let me know and I can change the key. All right, so that is Riemann sums in terms of a graph. In terms of a table, it says use the table to approximate the area under the graph of G between 1 and 4 with a left Riemann sum and the 3 intervals indicated by the table. Okay, the 3 intervals indicated by the table would be here is a rectangle between 1 and 2, here's a rectangle between 2 and 3, here's a rectangle between 3 or 4. Okay, to get the area of each rectangle, you would do the base, which would be the x values. So between 1 and 2, that's a height, that's a width of 1, times a height of, it wanted the left Riemann sum. So the left endpoint would be the one defining the height. So I'm going to look at this y value, this 5. That would be 1 times 5, plus next rectangle also has a width of, from 2 to 3 is a width of 1, and a height of left endpoint would be -2, plus 1 for the next one, because from 3 to 4 is 1, and then left endpoint is 0.25. Sorry, 0.5. Nice. Add all those up, and that'll give you your answer. This would be 5 minus 2 plus a half of 0.5. And then that's what? 3.5. 3.5. Yay. All right. Then this last bit about the definition of an integral. Remember how this looks. So we're trying to translate these sums into an integral from somewhere to somewhere of some function. Okay, so I think the easiest thing to find is the function first. The function is basically whatever is being multiplied by a fraction over n. So here's my fraction over n. This other factor must be my function. So it's 3 times something to the 4th minus 2 times that same something plus 2. Okay, now this ugly stuff in parentheses, that is going to be replaced by an x. So that'll be 3x to the 4th minus 2x plus 2. There's my function, dx. And then from where to where am I going? Well, remember your a value, your bottom bound, is the number being added to the fraction in parentheses. That would be a -1 in this case. And your b value is told to you by this fraction over n. So it's not going to be a 4 though, it's 4 more than your a value. So 4 more than -1 is 3. So here is this. Okay, if you didn't get that one, keep watching these other ones and you'll see the pattern. Okay, so again, I'm translating this sum into an integral. First, I find my function. My function is what is being multiplied by this fraction. So here's my fraction, here's my function. In this case, it's pretty obvious, like cosine is obviously going to be your function, but that I'm just trying to be consistent. So cosine of this ugly stuff in parentheses is always going to like turn into an x. Then you end it with a dx. And now from where to where am I going? Well, I got to figure out where I'm starting. So it looks like I'm starting at, I think this is written badly. Yeah, this is written really, really badly. This has some typos in it. This, first of all, should probably be a 2 plus this fraction. And then this pi over 4 should be a pi over n. I don't know why it says over 4. Okay, so those are some typos. If it looks like this, then it looks like I'm starting at this number, the number being added to the fraction. I'm starting at 2, and I'm ending pi after 2. So 2 plus pi. I think this is a kind of a weird one. First of all, it had some typos in it, and then the bounds are kind of hard. But there it is. That's that one. Okay, and then let's go backwards. Okay. So now we're taking this integral and we're writing it as a Riemann sum. So let me write you the general form. Remember that a to b of f of x dx. The general formula looks like this. It's the limit as n goes to infinity. That's the number of rectangles of the sum from the first rectangle to the last of b minus a over n times f of a plus a k rectangle widths. That's it, right? Length or width times height. Yeah, that seems right. Okay, cool. So then let's follow this formula. It looks like here I should have a limit as n goes to infinity, sum from k equals 1 to n of b minus a over n. So 4 minus 3 is 1 over n times my function evaluated at a plus k times that same fraction. My function is 1 over x, so that would be 1 over, and then a is 3 plus k times b minus a, so k times 1 over n. And then I'm done. You could probably simplify this because fractions within fractions are usually like not what you want to leave things at. But I don't think I want to simplify that. I think I'll leave it like that. Okay, and then this last one, same thing, limit as n goes to infinity, sum from k equals 1 to n of b minus a over n, that would be 5 minus 0 over n, so 5 over n, times my function, so times 2, evaluated at a plus kb, b minus a over n. So 2 times not x, but a, which is 0, so you could put a 0 if you wanted, but I won't, plus k times 5 over n, then plus 1, that's this plus 1, and then you're done. Nice. And then 30 is just a smiley face. We did it, you guys. We got through the whole thing. All right. If that still didn't make a lot of sense, then come ask us in person, and we will explain anything you need. Hopefully this helped, though. Make sure you study hard and be ready for your test on Friday. All right, goodbye, you all.